Hi, and welcome everyone to my talk, Unlocking the Power of Integer Programming, a Beginner's Guide to Conference Scheduling. So nothing beats a little bit of math, right, in the afternoon, but don't be afraid. Actually, the idea for the talk came during the PyCon, PyData in Berlin, and there we actually had this problem. How do we schedule our talks? How do we fit them in a real good schedule? And today I want to present you how we did it and a little bit of background. So before I start, a few words about my background. So I'm a mathematician by profession, and yeah, I've worked in the field of data science for quite some time, did a lot of Python programming, and I work for Innovex. We are an innovation quality-driven IT project house with a focus on digital transformation. And we basically have everything from application development, scalable IT infrastructure, and data department, data management and analytics, where I work in. And I would say enough advertisement. Maybe we start with the context we are in, right? So before I even explain what integer programming is, the field we are now in is so-called operations research. And the objective of operations research is the development and also the application of mathematical methods to support decision-making processes and agnostic to various fields. So it can be in manufacturing, it can be in finance. So you find the problem of operations research everywhere. A few of them might be common to you, like an assignment allocation problem, like the one we're going to dive into deeper. Like what if you have a schedule and some talks and you need to decide which talks goes into which slot and what is actually an optimal schedule in the end. Then you surely have also heard of transportation problems. Let's assume you own a few factories and you have suppliers, and those suppliers need to deliver goods to a factory, and you have a graph of streets, train, railways, and so on. And you need to decide which factory or which supplier needs to deliver the goods into which factory, and you want to minimize some costs because each street or each way of transportation has different costs. Another one is the shortest path problem. Again, assume you have some graph, some network, you have a sink and a source, and you're going to go from A to B, and each edge has some cost associated with it. And you need to find the one path with the minimal cost. Also, you surely know the trailing salesman problem. This was also mentioned in the morning keynote, which was really great about quantum computing. And another one quite related problem is the so-called maximum flow problem. Imagine you have a computer network or a pipe system, and you ask yourself, okay, here's my source, here's my sink. What's the maximum throughput through this system, or the maximum flow? And what all those problems have in common, that they are like real-world problems, and they can be solved mathematically with what's called linear programming. And the definition is really easy. So it's just some cost function. So we have some vector multiplied by some decision variable, and we want to find the one x which minimizes this. And there are certain constraints. So we have some matrix A times x is smaller or equal than some vector B. And our decision variable is some real vector of n dimensions. And how many of you have seen this before and know the simplex algorithm? Maybe some hands? A few. So one of the common ways to solve this is the simplex algorithm. And this is a quite complex algorithm. So in the mathematical complexity, so in the Landau symbolic, it's cubic. There are other methods like interior point methods which solve it in n to the power of 2.5. So still quite high if n is a large dimension. But in practical use cases, it works. And if you wonder now why it's called programming, actually, so this is more like a naming that happened in the 40s. So those techniques are really old. And when this one guy, I think he was called George Danzig, came up with this, that you can solve a lot of problems with formulations like this. It was war times, right, the 40s. So he had to decide for a cool word that describes basically what he wanted to do, like organize things, structure things, plan things. And this programming meant planning back in the day. And he named it linear programming because this sounds more applied and he could get his funding to do math, actually. So a little anecdote about why we call it still linear programming, although it's basically an optimization problem. So now adding one more additional constraint makes this problem a lot harder. So if I now say that some of those components are no longer real numbers, but integers, then this problem is no longer in a complexity of cubic. It's now suddenly NP hard. And so the complexity grows exponentially. And this may sound counterintuitive because in a way we kind of limited the possibilities, but it's now way harder, and just dropping this additional constraint, you might think, just forget about it. We solve it with a simplex algorithm, and then when we get an answer, we just take the nearest integers. So this will not work in practice. So a few more special cases of those integer programming or mixed integer programming so we talked about the linear case. There's also quadratic case, which makes things more complicated. In many cases, it's not mixed, so you only have integers in your decision variable. Then it's called an integer linear program or just an integer program. Or in our case, in our use case that we're going to get to, it's actually a 0-1 linear program because we're going to only decide if a talk is in a certain slot, yes or no, so 0 and 1. And no talk about integer programming or linear programming without the hello world. And I think this the hello world of linear programming, and I think this really shows nicely this kind of translation from real-world problem into a mathematical formulation. So assume you are given some items, or there's many items in front of you, and now you need to select those items that you can carry. And of course, you can carry only up to a certain weight. And you want to maximize the value of the items you take with you in your Knapsack, so in your backpack. And we can now easily translate this kind of use case in our normal language into math by saying, okay, so the decision variable x is now 0 or 1, right? If we decide to take this item with us or if we leave it there, then the value that we actually take with us is the value of the item multiplied with if we take it with us or not, so 0 or 1. And of course, we sum over all the items that are there. And the same we do with the weight. And of course, it needs to be smaller than the maximum weight limit we can carry. And you will see that basically what you do in all those operation research cases, or in our use case with conference scheduling, the actual challenge is to translate this into these mathematical formulations, and then we have methods to solve it. And I want to mention the concepts of two ways to solve this mixed integer linear programs, because you might wonder, so didn't he just say it's NP hard, right? And NP hard means that even in low dimensions, it's impossible to solve. So how it's done, how it's actually done. So there are two heuristics which work really well in most use cases, called the cutting plane methods and the branch and bound methods. And most often you will see them combined as branch and cut methods. So just the basic ideas. So the cutting plane methods starts by just forgetting about the additional constraint. You solve the relaxation problem, and you have a solution. In most cases, the solution will not be integral. So you will have real number, but no integer number. And what you do now, you add additional constraints that exclude the found solution, but no integer points. And then you solve again. So this sounds quite complex. A simple example. Let's imagine we are in 2 dimensions. There it's easy. We can just visualize it. And the constraints can now be nicely translated into lines, into hyperplanes. And all the feasible solutions, these are the bright blue ones, are within those or between those 2 lines. And our cost function, so the isocline here is just in a way orthogonal to the normal, to the 1, 1 vector here. And the optimal solution is 2.2. So this one here, because it's within the 2 lines and to the upper rightmost edge. But let's assume we don't know this. So what we would do, according it, we would relax by forgetting about the additional constraint. We solve it, then we end up here at one of our edge points, corner points. This is what the simplex algorithm would found. We add an additional constraint like x2 is smaller or equal than 2, so another line, and we solve again. This time we end up here. We add one more constraint, and now you see, okay, the simplex algorithm will find us a solution that is integer. So this is already the basic idea, and as you might guess, the real magic part that I left out is how do you come up with smart additional constraints. But this is way beyond the talk, and there are many heuristics to do this. The other one is branch and bound. Also this one is simple in principle. So we solve again the relaxed linear problem by forgetting about additional constraint. And for a component that is not integer, we define another subproblem by saying that x1 should be smaller than the solution at that point, rounded down, so the floor, and 1 for rounded up. So in the end, we build a kind of graph of subproblems. And we can now eliminate certain branches in this graph by applying this simple inequality that we know that a feasible solution by definition is of course smaller or equal than an optimal solution. And an optimal solution, so this is the interesting part, is also always smaller or equal than the solution of a relaxed solution. And whenever we find in one of those sub-branches that a relaxed solution is smaller than one of the feasible solutions we have already found, then we can actually say, okay, there's nothing interesting to find here anymore. And by this, we can exclude certain combinations. So this is basically the trick used in many solvers to solve integer linear programs. So now let's come to our use case. So assume we have hundreds of talks, like here at the code.talks or also at the PyCon PyData, and we have some schedule, and now we need to decide which talk goes into what room, on which day, in which session, and which slot in the session, and so on. So let's first think about what kind of constraints do we actually have. Of course, many are quite simple, so each talk must be assigned exactly once. So you don't want anyone giving the talk 2 times at the same conference. Then each room time slot combination can also only be occupied by 1 talk at most. Makes also sense. The length of the time slots must match the length of the talk. This also makes a lot of sense to use the time most efficiently. And then at PyCon, PyData, we also had tutorials, and they had a part 1 or 2. And of course, you don't want them in the wrong order, and you want them consecutive, right? So you also need to make sure to guarantee that. So what is our objective? And here it gets really interesting, because this is the point where we can put in our knowledge to make a schedule more interesting for our audience, and we can really start optimizing. So first of all, there's always keynote speakers or speakers that are only available at certain days. So they tell you certain preferences, and you want to, of course, make sure that those preferences are met. So some speakers can only speak at certain days or in the morning and so on, and you want to make sure this works. Then what we also had is that we had a poll where we asked people what kind of talk would they want to attend to way before the conference. So we already had some kind of popularity of a talk, and by having the popularity of a talk, you could, for instance, make sure that the room capacity fits the audience who wants to go to this talk, so that you don't have a case that there are not many people in a big room, right? And then with the same information, you can also avoid parallel talks. So let's say many people said, I want to see talk 1 and talk B. And if a lot of people want to see them, of course, they should not be in parallel, right? They should be at different rooms at different time slots. And then you can also think, okay, we don't want to have people run around so much in between talks. So maybe people are interested in the same tracks. So we had a track for PyData talk, for PyCon talk, and we want to make sure that one session, so 3 slots, that they are optimized in a way that they are only one main track, if possible. And then lastly, we also had subtracks like PyData data handling. And this, if possible, it would also be nice to have them the same in the same subsession. And now we have like 5 objectives, right? So what do we do if we have 5 objectives that we want to optimize and which may be conflicting? We have to give them some kind of order. And we decided that the preferences are most important for us, then the popularity and so on. And we will see later that this can be achieved by multiplying the terms with large numbers. So now that we had an idea, okay, this is how we're going to tackle the problem, what software can now help with this. And I'm a huge fan of Python, as I said, and open source software. So we made a little research and find that Pyomo and Pulp are quite common ones. I must say that I like Pyomo more, so I started to implement it in Pyomo. And Pyomo basically, and all those frameworks, they allow you to formulate your problem, and then they translate your problem into some standardized format. And this standardized format can then be read by different solvers to actually give you the results. So this is a nice way of splitting the problem up between formulation and actual solving. And as a solver, also wanted to keep it cheap. There are a lot of commercial solvers available for a lot of money, but also some open source ones. And that shows this Higgs or Hikes open source solver. So just to give you a little idea, I know it's always bad to show source code, but just an idea, to give you an idea, how this looks in the end. So we have a lot of index sets, like for our talks. This was like the 100, I think it was 20 or so talks. Then we have the 3 days. For the 3 days, the conference was on. Then we had potentially up to 4 sessions, morning 1, morning 2, and so on. Each session has 3 slots potentially. Then we had up to 7 rooms and the 2 main tracks and a lot of sub-tracks. And you can already see that in the end, the dimensionality is already quite high, because it's like 7 rooms times 3 times 4 times 100 something talks. And it even gets more, as we're going to see later. So now the parameters, and the parameters are the part where you kind of, they're going to later make up the matrix A, or sometimes also the C in the cost function, so the matrix or the vector. And just to show you the parameters for the preferences of the speakers, here we have those codes are standing for one talk. That's just some internal representation. And for instance, those talks, they wanted to give their talk on a Monday because they were only available on Monday. And this one talk could also be held only on Monday morning and so on. And this is how you initialize your parameters. Then the actual part, the decision variable. So this is the only variable in the end we are interested in. So this is a variable over the talks, the days, the sessions, the slots, the rooms. And they are 0 or 1, meaning, yeah, by looking at this, you can say, okay, for only this one single talk, there's a certain day, a session room where it's assigned, and for all the other, it's not assigned. And then we need a lot of helper variables, like, for instance, is talk assigned to a certain room? And you need those additional ones, and they're going to make up a lot of additional variables in the end, because with them you can help to define your constraints. And the constraints, for instance, let's start with a really easy one, the constraint that each time slot combination is only occupied by a single talk. We can do this by going over all possible combinations of days, sessions, slots, and rooms. And then we sum over our talk dimension here. And this needs to be smaller or equal than 1. So it might be that, that there's no talk assigned yet, or that we don't have enough talks. But we want to make sure that this is not 2 or more talks assigned to the same time and space. Another one where it gets more interesting is if you make sure that the talk length fits the slot length. Here we use the schedule. We multiply it with the slot length. Again, here this is only 1 now in for a given talk at one combination. And if you multiply this with the slot length, then it should be the talk length for this talk. And you might now think, hey, well, this looks, combination looks, or this kind of formulation looks way more complicated than I would have written it, maybe in Python. This is all due to the fact that we have to make sure that the constraints are linear. So you cannot do certain things like multiply different variables with each other and so on. You have to make sure everything is linear. Then now the actual objective. So the objectives we talked about before, you basically translate them to several terms. So we have the preferences if you multiply them with the schedule as a dot product. And this term, we said we want to make sure that it's really the case. So we just multiply it with a really large number. So that a little change here will improve drastically our objective. And in this case, we maximize. And the same goes for the room capacity. Here, we formulated it rather as a penalty. So if we put a talk with a high popularity into a really small room, then we get a high penalty. So this is why we subtract it here, because we maximize this. And also for the co-occurrences, it gets a little bit more complicated, but I think you get the idea that in the end, we take all the helper variables, all our decision variables, multiply them with the right parameters, and sum them up. And just to give you an idea, so it looks not really impressive in the end, what I got as an result. So those are the different rooms we had. The last 2 rooms were reserved for tutorials. And if you wonder about another number, this is just to the fact that this are always tutorials over 2 slots. And this we wanted to keep free. So we had the different codes for the different talks. And yeah, this was basically the result that optimized all the possible combinations that you could think of by just assigning talks to the different time slots. And if you're interested in this, so even more details, talk to me later, of course. But you can also check out a notebook where we have the whole code. It's all open source. And we also released the library Pythanis, which is also open source, that helps to organize community conferences. So everything's open source. So you might find, well, that sounds all easy enough. But is it really? Just to give you an idea, what sometimes really like a brain twister in a way is that even if something really easy like an absolute value, you want to say that A minus B and the absolute value, so the deviation in a way, this is not linear. So if you need something like this in your objective, you have to reformulate it, to linearize it. And how does this work in case of the absolute value? So you can introduce a new auxiliary variable, or even 2, so T1 and T2, an additional constraint that T1 minus T2 is X. And what this means graphically is just, if you think of this as X, then you express X as either, if you're here in this quadrant, it's T1, and because T1 is 0 here, and just X here, or minus T2 here in this case. So either one of them is 0, but the other one will be the negative or the positive part. And now you can just flip it around to the absolute value by putting T1 and 2T in your min objective instead of your absolute value. And there are many tricks like this. If you design a problem as an integer problem or a linear program, and this is actually the hard part and also the reason why in the end you end up having lots of constraints and lots of additional variables that make your problem even more high dimensional. So to sum up the main takeaways, so we learned that mixed integer linear programs are an important tool in the domain of operation research. Of course, there are many others. That many optimal decision problems or use cases can be reformulated as a mixed integer linear program. We also learned that it's NP hard. And yeah, but there are good heuristics to solve it, or we wait for quantum computing. And we also learned that Pyomo is one cool tool that's open source that translates your problem into a standardized form where it can be solved with a tool like Higgs. And the hardest part in modeling this, or when you kind of get into, like I did, like get into this field of mathematics and to use it, that the hardest part actually is to make sure that everything you formulate is still linear. And with this, I want to just mention a few of the references. Of course, it's not that I invented all this, so I also read it up. There are many cool tutorials about this. Just look them up later on. I'm going to post the slides. And with this, I want to say a big thank you. And yeah, looking forward to your questions. Thank you.